What's up everybody, today we are going to talk about extended Kalman filter, which is a type of nonlinear observer. Alright, and we are going to look at extended Kalman filter by using this very good example from the book. This book is called Nonlinear Control. The author name is Hasan K. Halil, and of course famous author, right? And Global Edition, Pearson, 2015. Alright, and okay, in chapter 11 we have nonlinear observers covered, right? And the first example that was discussing extended Kalman filter, and I thought that would be a really good tutorial video to talk about extended Kalman filters, right? And okay, first of all, you have the given form x equals f of x u, right? You have some input, right? And then you measure your state through this measurement function called h, right? And you have y, you have this output signal, and what you want is to reconstruct in real time, by the way, right? Not like we can just employ MPC type of algorithm for that, right? And because otherwise that wouldn't be, I don't want to go into the philosophical details of that, but that wouldn't be considered as real time, right? All right, let's not talk about those type of details. And here we can see the typical observer form, right? Okay, what would you do? You would just copy your state equations, right? State dynamics, and then of course you would substitute x hat for x, right? And then this is called, let's not worry about that, but you would have y minus the output of your estimator system, or maybe we can call this, you can have this error term, which is the error of output, error between the output of the real system and the output of your model system, right? Estimator. Okay, and the output and estimated output. Okay, and by using this error, right, you can have some type of idea. Hey, if this error, for example, is, I don't want to give that example, but it is almost like contour. I have serious problems with saying that, but there's a strong connection, right? And but I feel like some people say this like observer is a type of control, but you kind of use this as an excuse to not talk about observers at all, right? So all right, I'm just wanted to say that. And by using this error term, this is an information. Okay, this is an information. Let's talk about in simple terms. If this error term is small, what you would think about that? Let's not talk about if it is true or mathematical details, etc. But what would you think? You would think, hey, my estimator or my observer is probably doing a good job right now, and right, and what I am estimating, the state estimates, right, and they should probably converge at this point to the real state of the dynamical system that I am interested in, right? You would think that way. And so hence the form, right, we have. All right, but for linear systems, this h, you would have some type of gain term, right? And for Kalman filter it is called Kalman Gain, right? And you would have this gain term like in the k in LQR control, right? Okay, again there is a strong connection between LQR and Kalman filter, right? Okay, wanted to iterate that. And what I want to say is that you can have a constant H matrix, let's call it H matrix, or constant gain term, right? If your system is LTI basically. However, you cannot do that all the time. Of course, you can. I mean, there are some nonlinear dynamical systems where you can again employ constant H matrix. Okay, that's all right. And by the way, let me tell you this: the condition if you can employ constant H for a given nonlinear dynamical system is the linearization, right? For example, you have nonlinear dynamical system here. This is nonlinear, right? And you are going to get A, okay? And this just, I mean, A, right? And C is, let me type it real quick. Okay, all right. Again, this A and C, X equivalent and X equivalent, right? This, and also maybe U equivalent, right? This A and C, at this point, they are constant matrices. And if pair AC is detectable, then you can have this for some cases. Not always, again, right? Because, I mean, if we are talking about nonlinear dynamical systems, all base are off, right? So we cannot just say every time you can do this or something. It's not that easy, right? No free range. All right. So you need to have time varying H term if you have nonlinear dynamical system. Again, let me preface this by saying you cannot just design extended Kalman filter for any type of nonlinear state estimation problem, right? And or nonlinear state estimation problem for a given nonlinear dynamical system, right? Because I mean there are underlying assumptions that you do or construct extended Kalman filter and the resulting system working properly. There are some underlying assumptions, and one of them being, for example, the norm of x error, right, or the initial, right, starting point in a way. This is x tilde, right, and it is x tilde is like x minus x hat. Okay, so if your initial error is like small, yeah, you can do that. But even in that case, you cannot 100% guarantee that extended Kalman filter will be able to, estimate the states without any problem, right? Okay, so, but to me, if you ask me, and if you ask, I guess, any type of observer, designer or something, right? Professional, not like me, by the way. And I have a strong feeling that they would probably say, okay, just start by designing an extended Kalman filter, right? At least see where this is going, right? Okay, it is not a bad idea just to, because I mean chances are it's not going to take a lot of your time, right? Okay, all right, out of sidetrack topics, and what I'm going to do in this video is I'm just going to look at an example and we're going to design an extended Kalman filter, and we are not going to, right, we are not going to talk about the theoretical why this is working, why this should be working, etc. We are not going to talk about this. I am just going to give you, right, the, I guess, the formulas or something, or set of equations, and quick way for you to, construct an extended Kalman filter and simulate it. We are also going to simulate if it is really working, right? Okay, all right, so we have talked about this and we also talk about this, right? All right, that's great. And this is the example that we are going to look at. Again, took it from that nonlinear contour book, right? Hasan K. Halil, right? All right. And there are basically 5 steps, meaning we will have almost like 5 formulas to, I guess, write down on a piece of paper. Okay. Okay. So step 1, I named step 1, step 2, 3, 4, and Wow, it's not even 5. I'm sorry. Where did I get that idea? I don't know. Anyway, just 4 steps. Okay. And first step is this formula, basically. Just linearize that nonlinear dynamics, right? And this sub x hat means substitute x hat for x. Okay. Again, I'm 100% sure that you know what that means, but again we are going to look at that example and we are going to do that, right? It's not going to be a problem. I can guarantee that you are going to learn it and will be able to apply for your hopefully not so high dimensional problems. All right, it's gonna work hopefully, right? Okay. And again, for same for the output matrix, right? Measurement matrix. Okay. And here this is just the Jacobian, right? Okay, Jacobian of that f with respect to x state. All right. And again, the Jacobian form. All right, we know already what it is, right? Okay. It's not something, for example, we are not going to learn something new here. Something fundamentally new to, right? Construct X and Kalman filter. All right. Step 2. Again, we are going to talk about this. There are 3 terms. Q here, they will be matrices, by the way. Okay. If it is not like CISO or something, right? There will be matrices. Q matrix, right? P of 0. And from that you can kind of say, hey, I guess we will have a term like P of T or something, right? Okay, yeah, that's correct. P of 0. And those 2 guys, right? And we'll have the dimension of n by n. Okay, and n, by the way, n for state, right? Dimension. M for input dimension and P by output dimension, right? Okay. Just wanted to, make that clear. And R matrix. Again, P by P, right? And for example, if you have one output, which we will have in the next example, we will have 1 by 1, meaning a scalar R term. Okay. And by the way, a quick note here for this step, we can just start by, I guess, assigning identity matrices to them. Okay, it wouldn't be a bad idea. Just try it. Okay. And step 3, p dot dynamics, write them down explicitly. Okay, you don't need to know, right? For example, things about algebraically cut the equations, etc., or matrix differential equations. But we have this formula. You can just take it for granted, or I feel like, right? Okay. And for example, this A is this A, by the way, right? And this C is this C, right? So at this point, we also going to talk about the structure of P matrix. P is matrix, right? And of course, I dropped of T. For example, I could have written A of T, right, times P of T, capital P, by the way, right? And but Q is constant, right? And R is also constant. But other terms, they are time dependent. And A of T has X hat in it. Okay, and that's why X hat is time dependent, and that's why A of T is time dependent, because it's through X hat of T. Okay, got it. It's all, again, it's all going to make sense. Just take a, walk if you have some problems with that, if you have some stress problems. All right. Okay, therefore X hat dot dynamics, right? And again, write them down explicitly. And this is again the type of nonlinear observer form that we looked at, right? And h of t, again, we want to find, this is the only thing that we want to know at this point, right? H of t is this, given by this expression, and p of t comes from this, let's say, dynamical system. And you can consider we have another dynamical system, and p of t is its state. Okay, all right. And c of t, we know what it is, and r inverse, we know again what it is. It's something that we are going to choose, right? Okay, and let's look at this example at this point. Here, design an excellent Kalman filter for given nonlinear dynamical equation, right? And first step, let's remember. By the way, I forget to write this. Let me not forget again. Okay, y the measurement is only x1. Okay, c is so c has that form. So c doesn't depend on c, right? Okay, for this problem, I mean, I could have picked another example, and I feel like it would have an adverse effect, because my primary goal is to make this simple and get the point across, right? But there is, of course, if I picked a like really simple example, of course it would again have an adverse effect, and I feel like that's why I like that example. That's a good balance, right? Okay, so a of t, again, we are familiar with this term. This is Jacobian, right? And let's, wow, I didn't write that, by the way. Okay, you know what? Yeah, I remember. Yeah, let's go to MATLAB, right? Let's go to MATLAB. Let me just click on it and control up. Okay, here, let's clear the screen, right? So I can see that you're able to see the screen, right? Okay. All right, this is symbolic variables x1, x2, right? And again, this is the problem. And by the way, let's go to tablet again. Let me pick another color. All right, this term again, there is no x1 or x2 terms in this expression, in this term, right? So you can consider it like a input, right? And this is, and again, sinusoidal term. And okay, so I am not going to write that, because again, you can consider it like input, right? And because I mean, there is no x1 and x2, so again, look at the formula, right? So it won't be a problem. Okay, it will make sense at the end, right? I promise. Okay, so okay, f1 and f2, right? Here and here. Again, there is only that you can consider what I called input term, right? Sinusoidal term. But since there is no, yes, yeah, okay, we are going to talk about that. Since there is no state in it, and we are only using f1 and f2 to create this Jacobian a of t term, it won't be much of a problem for us. Okay, so let's, and wait a sec, let's run it. Okay, and what was the other step we also need to do? You remember, we need to substitute x hat for x, right? Okay, so you can just use wait a sec, yeah, forget to run this section. And okay, so this is our a of t, right? This is our a of t. Okay, all right, let's go to okay, let's talk about step 2. Step 2, we have b and c, right? And since that sinusoidal term only appeared in x2 dynamics, that's why we have that b, and I consider that as like an input signal, right? Okay, and or you can also consider this system as being like a nonlinear but time varying dynamical system, right? Okay, here b and c, they are just system dependent terms. B matrix, input matrix, and output matrix, measurement matrix, right? And step 2, decide q, p of 0, and r. P of 0 we are going to use it at the end, right? Okay, but again we can just assign identity for them. Again, m by n q, that's why it's two-dimensional, because we have, I mean, it's okay, two-dimensional dynamical system, right? We have x1 and x2, two states that we need to worry about. All right, again we have only one output signal, and that's why here that explains the dimension of R matrix. Okay, so let's look at, okay, let's go to tablet, right? So there are some analytical things to discuss. All right, step 2, and now we are here in step 3. Okay, let me get you. Okay, here, first of all, we have A, and we know what A of t is, right? We just created by using symbolic toolbox of MATLAB. Okay, and P matrix is here, has that form. Again, are written P12 and again P12 because it needs to be symmetric, right? And again, I guess I forget to say that here Q, P of 0 and R, they all need to be symmetric and positive definite masses. Okay, all right, and Q, again, it's a parameter that we need to choose, all right, and we chosen as identity, all right, and we know what it is, and also R, again a parameter. Okay, so we need to just write down the dynamics of P matrix, right, using this algebraic reconstruction. All right, let's try to do that. Of course, wait a sec, just look at this expression. I mean, this is, even though it's like two-dimensional problem, you kind of know how laborious the things might go, right? Might get. Okay, and that's why we are going to use symbolic toolbox. All right, so here let's define P11, P12, and P22. We only need two terms, right? Because it's symmetric, and that's why we lose like 1 degree of freedom, right? And here, this is our P matrix. Here it has that form, all right? That's great. And since we know what A of t is, again, let's display it, all right? And this is the formula, all right? This is algebraic equation. Here, this is Q, and this is basically that formula. So P dot term is like 2 by 2 matrix, and each entry composed of, each entry includes one of the following variables: P11, P12, P22, x1 hat, x2 hat, right? Okay, so let's, yeah, I forgot to run this section. Let's run it. And again here, okay, wow, what a mess this is, right? Okay, it's almost there. Wait a sec, I'm determined to show you this. Okay, all right, P dots. First of all, don't distracted by how long this expression is. Okay, doesn't mean a thing, right? And again, it needs to be a 2 by 2 matrix, so also be aware of that. Here, this is P11 dot. This term, basically, you are going to take that and you are going to write as like P11 dot and equals to sign, and then you are going to like copy and paste this. All right. And by the way, this is something that we're going to do in a minute, right? Okay, and this is, by the way, of course, this term and this term, they're like same because P is symmetric and P dot needs to be symmetric because of the structure of that algebraic equation that we look at, right? All right, so basically this is P11 dot, or P11 dynamics can be explained by this formula, right? And this is P12 dot. P12 dynamics can explain by this equation, and this is P22 dot. Okay, all right. seriously, we are just going to copy and paste it. Now we are going to conclude our extended Kalman filter process, design process, and then we are going to, of course, check it if it is really working properly by using OD45. Anyway, what I was saying, yeah, we are going to use OD45 to simulate the real system, okay, two-dimensional real system, and then the dynamics of those, yes, P matrix, okay, that's a parameter for our extended Kalman filter, and then the dynamics of our observer states, right? So just, I guess, think about this. For example, we will have two state dynamics, state of our real system, I mean quote unquote real, right? Okay, x1 and x2. All right, and then here we can see that we need to have like one, wait a sec, 1 here and 2 and 3, right? We need to also have like 3 states, P11, P12 and P22. All right, of course, state like quote unquote state, you know what I mean. And then it's like, so it's 5, 2 plus 3 equals 5, and we also need to have our observer dynamics, right? x1 hat and x2 hat, right? So 2 plus 3 plus 2 equals 7. Yeah, it's going to be a 7-dimensional system, the general system that we are going to simulate by using OD45. All right, let's try to, where's cursor? Yeah, okay. Okay, so by the way, you can just get, yeah, here like first row, first column, right, of this p dot matrix, and this symbolic expression is like the p11 dot basically. Okay, and again you can do the same for p12, p22. You can just display them, right? Let's display p12 dots. Okay, this is p12 dynamics basically. All right, and this is p22. All right, again, wait a sec, I forget to mention here we can see, for example, in p11 dots, yeah, just like p11, p12, but for example for p12 dots we can see, okay, p terms, but also, well, x1 hat and x2 hat, right? X hat terms basically, and again same goes for p22 dot terms. All right, it's all coming together. All right, so let's go to tablets. Okay, here this is something that we just talk about by using symbolic toolbox of MATLAB, right? Okay, and we needed to construct those 3 dynamical expressions. Okay, and here, and finally we have step 4, what I call step 4, and where we need to construct x hat dynamics, right, by using this expression. And for this, the only thing that we don't know at this point is h of t, and for this we need to use that equation. H of t is this. Again, well, wait a sec, you don't need to write it on a piece of paper. You can just use similar toolbox MATLAB. Okay, so let's go to MATLAB again. Okay, right here, if you recall, that was the h of t equation, right? Okay, what do we have? We have we have a matrix, by the way, first of all, and we have 2 rows and 1 column, right? And that makes sense because it's like 2-dimensional problem, and we also have 1 output signal, output measurements, right? And okay, that's why the dimensions make sense. Okay, and let's get back to tablet because I wanna point one thing. Okay, so we know what this is. H of t is at this point, and let's construct x hat dynamics. Okay, wait a minute, I'm looking at the screen to see if I'm making anything wrong. Any mistakes? Okay, let's continue. Yeah, we need to change the screen, right? Okay, here first I wanted to look at this term, right? Like the second term in the general expression, x hat dynamics, right? On the right hand side, the second expression, and okay, and why x1 minus x1 hat? Because we had y minus h of x hat, and our y is like, due to our C matrix, we are only measuring x1, right? X1 state, and again we have the output of our observer is x1 hat because of that reason, right? All right, so let's try to construct x hat dynamics, and since in the like starting here we used x1 and x2, and we need to substitute x hat for x terms. That's why we are using subs command. Okay, here f1 and f2. It makes sense, totally makes sense if you think about that a minute. And this is the second term on the right hand side of that x hat dynamics. All right, so let's run it. Okay, for example, this is x1 hat and this is x2 hat. Okay, all right, and we are going to literally just copy this term and paste it in our function section of our OD 45 simulation that we are going to do now. All right, so you might think like, hey, I guess we are not done with this, but it's over. So we basically constructed our extended Kalman filter, and now we are going to run an OD45 simulation, and now it's all going to, all pieces going to come together. And first of all, I feel like you are familiar with this. This is like typical just run bunch of OD type of code. This is the code that I just copied and pasted to this script. I've been using this for whenever I need to use OD45 for my videos. So if you're like a subscriber and if you're watching a couple of my videos, right, it is something that you should be familiar right now, right? All right, so basically we have two states for our, I guess, dynamical system plant. Let's call it plant. Two states for our plant, and three states for our P matrix or P dynamics or P matrix dynamics, let's call it. Okay, and since we have two states for our plant and we are going to have two states for our x hat dynamics, so 2 plus 3 plus 2 equals 7, right? Okay, that's why we needed to like make this like initial condition, right? 7-dimensional. Okay, and since P of 0, if you recall, was like identity matrix, meaning P11 needs to, P11 of 0 needs to be 1, and P12 of 0 needs to be 0, and P22 of 0 needs to be 1, Okay, so that's why those three terms here appearing, right? Okay, let's focus on this part. This is the crucial part. Yeah, okay. First of all, this is x1 dot. Okay, this is just given by the problem, right? Okay, and this is x2 dot. Again, I'm just, you know, writing down the dynamics given by the problem, stated by the right book. Okay, and here that's like it. All right, writing down the same expression in a longer way, I guess. Okay, we are measuring x1. All right, that's great. And here, for example, if you look at this, what was it again? Let's go upwards. And here, this is x hat dynamics, right? And since we have like two-dimensional problem, we have two terms here. Okay, so what was it? This was x1 hat dot. Okay, x1 x sub 1 hat, because observer state, right? Hat. Okay, dot, right? And dot also because d over dt. Okay, all right. So we just copied this term and paste it here. This is literally what I did. Okay, all right. And here, this is x2 hat dot equals this expression, and that's why I copied and pasted here. I pasted here, but you can say, hey, we have also this term. We have also this term, and yeah, and I mean because we, for example, this is it. This and this, they are same. Okay, all right. But we also have this because, I mean, we know what it is. This is, we have the information about the structure of the dynamics, right? Or we have the dynamical model, right? And that's why I written that down. It could also be input signal, and that's why you would write that down. Okay, so I feel like I'm making this point, yeah, kind of messy. Let's look at this here. F of x hat and u, right? And so we are just going to let's look at the problem. And let's copy this, right? Let's copy and let's paste it here, and let's, if it is all possible, yeah, let's make it bigger. All right, that's great. So what is this? Basically this is f of x u, right? Okay, so just call it u. All right, okay, so we are just going to copy this and paste it right here, and step by step we are just going to delete x1 dot, and instead of that we are going to have x1 at dot. All right, so whenever we have x1, or let's call it xi, we're just going to delete it, and instead of, we are going to write xi dot, right? I is 1 or 2, right? Okay, so let's do it real quick. Okay, okay, I thought I made a mistake, but I didn't. x1 hat, x2 hat, okay, here x1 hat, okay, maybe it's going to be small, x2 hat. All right, this is it. This is this, and this is f of x hat u. All right. Again, input is something that we know, right? So yeah, this here, and we also, but we want to have x hat, and for x hat we have this, and right, what was h of t? I mean, I can't remember, it was made out of p terms. So this is f of x hat u, right? It's not x hat dot. So we also need to add h of t times this error, output error term. Okay. All right, let's go back to MATLAB here. So okay, that explains, I guess. Okay, this is x1 hat dynamics, and this is x2 hat dynamics. Okay. For example, I feel like if I did something like this, let me do that. I'm looking at the screen. If I wait a sec, delete, and if I did something like this, it would be a better form, because this is f1 of x hat u. Okay, and then we have h times, output error term. Okay, great. And here, what is this? This is x2, I'm sorry, f2 of x hat u term. Okay, and plus we have h of t times error term, right? And here, this is like h was something like 2 rows and 1 column, right? So the first term of our H matrix, like Kalman Gain matrix, was P11, and the second term was P12, right? Okay, that's why it makes sense. All right, and again, we have determined these terms by using symbolic toolbox, right? And here, let me show you. Yeah, do you remember this? Like, all of those are like, I mean, 20 lines of code, and not even 20, right? All right. So we have that. And maybe it would be better for me to just, wait a sec. Here, let's look at the left side of the screen. For example, this is P11. I literally copied and pasted down here, right? Again, this is P12 dot here. Look at this term and look at this term. I mean, I literally, this is what I did, right? I literally copied it and pasted right here, right? And same for P22 dot term, right? Okay, and they're same, right? Okay, and as we, remember here, two states for, it's like two memory points or something, right? For two memory points, for our state, like we have two states, okay, for our plant, and 2 for our observers, and 3 for our p matrix. Okay, comes from the algebraic equation that we talked about earlier. So this is the function, and you are able to see that, and this is the like script part. Okay, and I'm only going to run this for a time. Okay, let me run this. Okay, here. By the way, I am running this for x2. This is x2 here, right? It would be a great thumbnail, I feel like. And red is the true state of the system, and the green is our observer, and the error between those, states convert to 0, right? Okay, and let's do the same for x1, like x1 of our plant, and x1 hat. All right, let's do that. Okay, again, the error between them converges to 0, right? Okay. All right, I feel like it's all, but there is one more thing that I'm going to tell. Wait a sec. Here, I constructed this, produced that. Wait a sec. Okay, kind of a lecture note, like a cheat sheet for excellent Kalman filter design, and you can use that, and you can download it by using that GitHub link down in the description given below. Okay. Right. For example, I included everything that I just talk about in this video. Okay, again, the example, same example, right? Here you can see that. Step 2, decide Q, P of 0, R, etc. Here. Yeah, that's it. And I also added this MATLAB code simulation, right? All the 45 part of this code. Okay, right. And that's it for today, and thanks for watching.